And we're going to spend a little bit of time talking about actual real-life electrochemical cells, which we call batteries. So batteries are a fundamental part of modern life. We use them to provide electrical power in a portable sense. So everything from as small as, like, say, a watch battery to, the ubiquitous, say, laptop batteries that, power, literally kind of keep the object running. Car batteries, we think of like traditional say car batteries that cause the car to start, and then you run it on, or get the motor started, right? Get your internal combustion going. Or more modern, the actual batteries on, say, an electric car, where you replace the engine compartment with the entire bottom of the car, is a sequence of batteries. And so there's a lot of power in these. There's a lot of energy that we use to power things, make kind of modern society run in many ways. There's also a lot of danger in those batteries. There is a lot of very, very powerful chemistry that is underlying batteries. And if you don't kind of treat them correctly, or if they get misengineered, or if there are mistakes, you can have that chemistry happen really aggressively, uncontrolled. And then you can have some really, really dangerous situations, generally associated with, fire, explosions, kind of dangerous situations, flaming toxic chemicals, never a good thing. So kind of our standard, if we take something like a AA battery, and we kind of look at a cross section of it, it looks something like this. And we have all of these different parts that are labeled in this schematic. And there's a lot of different parts, but there's really three we want to focus in on. We have our zinc anode, the ion conducting separator, and the manganese dioxide cathode. And we can see that these are really just the three parts of the electrochemical cells that we've talked about: anode, cathode, and then just a fancy way to say salt bridge. Ion conducting, that kind of sounds like salts. Separator is the bridge. And so basically you have, the idea is you have the anode, which is this kind of light gray part in the schematic. That is going to react with the cathode, which is the dark gray part over here. And basically they are separated by this ion conducting separator. So what ends up having to happen is, in order for the electrons to flow from the anode to the cathode, they have to go through this pin. They would go out through whatever circuit you run, blah, 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 and then come back into the positive connection where they could flow into the actual cathode. So it's still from the anode to the cathode. You've just put that anode and cathode part into the same device or same kind of casing, and they're separated by that separator. And in all honesty, the main way that batteries fail is if that separator breaks, because the whole point of the separator is to separate the anode and the cathode, so that way they can't react. The flow of electrons has to pass through the wires or whatever device is connected to your battery. If that breaks and all of a sudden, they can react just directly with each other, you're going to have a bad time. If we take a look at the actual chemistry, the cathode, the reduction reaction, is a manganese-based process, and the anode is a zinc-based process. The reaction in these alkaline batteries is hydroxide-based. So alkaline batteries, alkaline, you'll note it's basic, so everything's under basic conditions. One of the things why we use this particular set of chemistry is, you'll note that those hydroxides cancel when you go to coming up with the overall reaction. One of the really important things about that is, when the reaction happens, it doesn't change the pH of the internal mixture, anything that's going on, and it's all solid, 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 which leads to basically Nernst equation doesn't really, you're not having like a reaction quotient Q that you need to necessarily worry about, and the chemistry is a bit more stable. You're dealing with a bunch of solids as opposed to a bunch of solutions that are going to be changing their concentrations really aggressively. Overall, you get a standard cell potential of 1.5 volts. That's locked in for alkaline batteries. So an alkaline cell based around this chemistry puts out about 1.5 volts, fairly kind of static or kind of consistent push. So what's the delta G be for this process? Okay, so I want to know what the delta G naught, my kind of standard Gibbs free energy change for a brand new standard alkaline battery. Well, if I'm looking for delta G for reactions, I have two different kind of reactions that we've seen previously. We know that delta G is related both to cell potential and equilibrium constant. In this case, we're dealing with a battery, so cell potential is probably going to be more useful. N is 2, the balancing we could see from the previous page. Faraday's constant is a constant value, and then I just gave you the standard cell potential, but you can also look it up. For those are standard half reactions. You could look it up. If you plug it in, you can see that delta G is pretty sizable, negative 290 kilojoules per mole. This is quite a spontaneous reaction, which we would expect considering the fact that those electrons are pushed. Batteries work, and they are quite negative. There's a lot of kind of push to drive this chemistry, to drive those electrons via chemistry. So a lot of times the 1.5 volts of a cell isn't enough. So how you actually get more potential or more voltage is you just put multiple batteries together in a sequence. That's why you potentially need to use multiple batteries in, say, a device. Sometimes they're also packaged as a product as it is. So for example, if you buy a 9-volt battery, that is just 6 basically smaller batteries kind of put together in sequence, or put in series would be the technical term, but you just do 6 of them, that multiplies the potential, you get 9 volts. So that's how you drive a 9 volt. These potentials of these cells will still decrease as the reaction progresses. That's what the Nernst equation says always happens. Your potential always goes down. And so that potential starts to fall. So the thing is, in order for a battery to kind of, quote, die, the potential doesn't have to drop to 0 volts. It just has to drop too low to push electrons through your device. So for most applications of alkaline battery, when it dies, there's about 1.3 volts of potential that is still pushing. So the battery still has chemistry. There's still a push for electrons to flow, just not enough for your particular application. What this corresponds to is 99.9999% of reactants are consumed. So you really are exhausting the chemistry in there. Almost all the reactants are gone, but there is still a lot there. This also kind of goes to show why you shouldn't throw batteries away in the garbage, because there's still a lot of chemistry to be had there. There's still a lot of chemical reactions that can still occur. There's still a lot of nasty chemicals that are inside there that are driving that chemistry. Another very common type of battery is the lead-acid battery. So first off, different by being an acid battery. So all this chemistry is happening under acid conditions, and it's based all around lead. So anode, we go from lead to lead 2. And in the cathode, we're going from lead +4 down to lead +2. And it's all happening in basically a sulfuric acid solution. So the overall chemistry we can see right here, lead basically reacting with itself, and the overall cell potential is about 2 volts. So you will note that this does change the pH, because you'd be reacting acid basically in the process of doing this. So there is, you'd have a ton of acid when you use these batteries to prevent that change. So these are car batteries, is the application of lead-acid batteries, the battery of any car, that not just electric cars, but even a standard combustion engine to get the car going. And one of the biggest kind of reasons why we use lead-acid batteries in this context is that because the anode and cathode, you'll note everything is, again, it's solids, solids, and solids that are actually doing the chemistry. None of that stuff is dissolved in solution, and lead ions are actually really insoluble. The KSP is really low for all these lead salts that you're looking at. And so you can basically get multiple cells packed into one battery casing at a time. So in a given battery, there's going to be 6 cells basically linked together. So this would be one kind of component where you have all these plates for your anode and cathode, and there would be basically 1, 2, 3, so on and so on. They're all linked together with just basically the only thing that's linking between the different compartments is a wire or is an electrical contact. Each one, there is kind of this contained chemistry within each of those cells. So if you were to say cut open a real battery, I would not encourage you. I would never, ever recommend cutting open a car battery, because not only is there a bunch of lead inside the car battery, but you also had to drain a bunch of concentrated sulfuric acid out of this. Your newspaper isn't going to do that great, so don't ever do this. But if you were to cut it open, you would see something like this, where you have basically each compartment would be a 2-volt battery or a 2-volt cell, and you can see there are 6 of them. Overall, you get 12 volts, quite a bit of potential that you are pushing with this battery. Another major reason why we use lead-acid batteries in the context of, say, starting a car is because they're what are called secondary batteries, which is just a fancy way to say rechargeable. So after you basically, the anode and the cathode react, you lose your reactants. What you can do is if you basically just push electrons the opposite direction than the spontaneous direction, you can just make that original kind of reactants come back. You can kind of form whatever the initial reactants were. And so that means you basically have reactant, they become product. You can basically push back to regain some of that original reactant. So that's why we use secondary batteries in the context of starting a car. Once your engine is running, you can kind of use the power from the engine or the energy from burning gasoline to basically recharge the battery. A primary battery is something like a standard zinc manganese alkaline battery. Those once the reactants react, they're done. They can't be regained. This idea of whether or not a cell can be reversed is almost entirely a kinetics issue. It's not really the equilibrium. We know it can. You should be able to always go backwards, but it's basically a kinetic problem that like the atoms aren't touching correctly, or they've been changed in a certain way that they really can't undo those changes. So a standard alkaline battery is there are kind of rechargeable alkaline style batteries, nickel cadmium batteries that you can buy that you can then recharge, but they need like their own kind of device. It costs a little more. Some people think they don't work as well. So that's why we don't really use them as much as say the standard Duracell alkaline batteries or Energizer. No product, no product placements here. So what would be the equilibrium constant for say a fully charged lead acid battery? Well, when we're looking at equilibrium constants, if we're looking for it for a generic reaction, we have kind of these different equations and different kind of relationships that we've seen. But again, we're looking at a cell. We're looking at batteries, and so we can directly relate that equilibrium constant to kind of the cell potential. This is one of the reasons to kind of describe more and more as much redox chemistry as we can using the cell potential idea, because we can figure out the equilibrium constant just from a standard cell calculation, which you can do using a table. So rearrange our equation, plug in all of our values. They're a bit there, but we get, say the 2 comes from balancing, F is a constant, the potential was given, R is a constant, and the temperature we kind of assume is room temperature. So we get the equilibrium constant is 4.59 times 10 to the 67th. That is big. These are very, very product favored reactions. That's why we use, let's say, a lead acid battery. This chemistry really, really wants to happen. You want a ton of products here. That's why it's really powerful, and that's why you can get it to start a car. Final big type of battery is lithium-ion batteries. So lithium-ion batteries are the anode, you can see is a lithium being ionized into a cation, and the cathode is lithium reacting with this cobalt compound, cobalt oxide, to produce this bad boy. So overall, it looks just like you got basically lithium metal reacting with, say, this cobalt compound to make the lithium-cobalt combo compound. This is a little bit different in the sense that when you're dealing with a lithium-ion battery, not only are the electrons flowing, but the lithium ions are actually moving through the material. So there's through the battery itself. There's no salt bridge per se. You have this lithium conducting electrolyte here, but instead of, some sort of like electrolyte counter ions that are flowing through the salt bridge equivalent, it's the actual lithium cations that were being formed in the anode process. Cell potential, real big, 3.4 volts. This reaction right here, this anode reaction, really, really wants to happen. Lithium very much is happy to form a cation. So the main reason why we use lithium-ion batteries is because they're really lightweight. right? When in terms of if you're running a device, what you really care about is the number of electrons that flow. And when you're dealing with, say, a lithium, that's moles of electrons. So when you're dealing with lithium, the molar mass is really low. So you get 1 mole of electrons out of 7 grams of lithium. So that's 7 grams that you would have to carry. That's why we use lithium-ion batteries in things like cell phones and laptops, or something where you need lightweight applications. Lead batteries, for every 100 grams of lead, you get 1 mole of electrons. That is a way worse mass to electron ratio. So that's why we use lead acid batteries for like cars, where you don't have to carry it around. The car can kind of support it, and relative to, say, the engine, the battery doesn't weigh a ton. So that's the main reason why we use lithium-ion batteries. One of the biggest drawbacks, one of the issues with lithium, is this fact that the lithium ions are moving back and forth between the anode and the cathode. So what ends up happening is, say your anode is this material. Usually we use graphite. These blue ions are carbon atoms, that are forming these sheets. And basically you have these lithium ions, and as the kind of battery runs, these lithium ions will literally move across the material and go to the cathode. That would lead to something like this sort of open space, which would inhibit the kind of stability of this anode. As you start to lose lithium cations, it gets more and more unstable, kind of something like, say, a Jenga tower, right? It becomes more and more unstable. It is more and more likely that your anode or cathode will collapse under this and isn't going to be that stable. One of the things that means is you don't use the Nernst equation here, you use a related idea, but it basically is the same idea that as you start to discharge the battery, it dies off really fast. So yes, it may be 3.4 volts under standard cell conditions, but as you start to discharge, that voltage can drop really, really fast. And so you would need to, say, use a lot of lithium, or have a really, to really get that potential at a high level for an extended period of time to have an actual usable battery for a while. The other big issue is that there is pure lithium metal in this anode. We said that the whole reason why there's this really high potential here is that pure lithium metal is pretty happy to react and become lithium plus. If your lithium-ion battery breaks and that lithium solid, that lithium metal, is exposed to air, it's going to light on fire. So lithium-ion batteries, kind of when they first started to reach kind of widespread usage around 2000, you had some issues, say in 2000, 2005-ish, with, say, laptops lighting on fire, because the engineering, the design of that sort of protective casing around the lithium wasn't necessarily fully up to par for some of the lower, kind of more economy versions of these batteries, and you started to have issues. That's why there's regulations on, say, putting a lithium-ion battery on a plane. It is, a kind of something we need to be very mindful of. They are potentially a hazard that we want to deal with. They have a lot of utility, and they have a ton of applications that are very, very, very useful. But if you break that casing, you're going to have some problems. Lithium metal is not a good thing you want to be messing around with. Okay, halfway through the set of videos. Not too many ones, they're a little long. But halfway through the set of videos, looking for more questions on participation for 10, maybe in the next video. See you there.